Perpendicular lines and proving lines parallel. So we've talked briefly about parallel lines and perpendicular lines, and now you're getting the formal definition. Parallel lines are coplanar and do not intersect. So they must be in the same plane, and that concept's very important. They must be coplanar. So parallel lines are lines that they're in the same flat surface, and if you extend them indefinitely, they never meet. So in this picture, for example, line EA and line FB are parallel. They're in the same flat surface, and if you extend them forever, they will never meet. The reason that coplanar is so important to the definition is it is possible to have lines that never intersect but aren't parallel. Those are called skew lines. They're non-intersecting, non-parallel lines. Now, that may not make sense, but these lines are not in the same plane. Here's an example of skew lines. So let's take that line EA that we had just a moment ago, and let's consider that and the line BD, the one that goes straight up and straight down. Now, it may not be perfect here in the picture, but if I extended those lines forever, they would never meet, but clearly they are not parallel. So skew lines are not coplanar, and they never intersect. Perpendicular lines are lines that meet at a right angle, and the way we show that is a little box in the corner. That means there's a 90-degree angle. The symbol for perpendicular is an upside-down T shape. So in this picture, I could say that EA that line is perpendicular to AB because they meet at a right angle. This shape looks a lot like a cube, and in a cube, every edge, the edge lines, always meet at a right angle. So parallel lines never intersect. They're in the same plane. Parallel planes are just two planes that don't intersect. So we add one more definition, and I believe we've even mentioned this before, the perpendicular bisector. It does two things. It's perpendicular, and it bisects a segment. So a perpendicular bisector is a line or ray or a segment that bisects a segment. So take segment AB. Now you might be looking at line AB, but all I'm talking about is the segment part of it. Line L bisects AB if it meets at the midpoint. And if it's perpendicular also, keep in mind this is the midpoint. If it meets at the midpoint and meets at a right angle, it is the perpendicular bisector. So there's two things you know from a perpendicular bisector. It's perpendicular and it bisects. In geometry, we define the distance from a point to a line as the length of the perpendicular segment. This concept's actually important, but we do it naturally. If I have a room and I have a floor and a ceiling, and I want to measure the distance between the floor and the ceiling, I of course do it along a perpendicular, straight up and straight down. So we always measure distance, the shortest distance, and that's what we're looking for, along a perpendicular. If I have a point and a line, and I want to measure the distance from the point to the line, then I always will draw a perpendicular to the line. And this distance right here would be the distance from the point to the line along a perpendicular. In the last section, we talked about all the theorems that occur when you have parallel lines. Now, it's important you understand, in the last section, we said if the lines are parallel. If the lines are parallel, then corresponding angles are congruent, alternate interior angles are congruent, alternate exterior angles are congruent, and same side interior angles are supplementary. Keep in mind, We started with parallel lines. If the lines are parallel, then all these things occur. Well, in today's section, we're turning that around. We're asking, what would make parallel lines? Well, they're the same exact angles. If corresponding angles are congruent, then the lines are parallel. Notice the hypothesis and conclusion are different. We flip them. That's called the converse. In the last section, it was if they're parallel, then the angles are congruent or supplementary. In this section, it's if the angles are congruent or supplementary, then the lines are parallel. That's why they use the word converse here. So when we name this theorem, you can just say the converse of the corresponding angles postulate. The corresponding angles postulate started with the lines being parallel. The converse starts with the angles being congruent, then the lines are parallel. So all those same angles occur here. If corresponding angles are congruent, then the lines are parallel. If alternate interior angles are congruent, then the lines are parallel. If alternate exterior angles are congruent, then the lines are parallel. If same side interior angles are supplementary, they add to 180, then the lines are parallel. Every one of these has a converse attached to it. And note, this is super important, you got to know this, the conclusion is the lines are parallel. So what we are doing is using this to show lines are parallel. That's why it's the converse. Along with those theorems that prove lines parallel by using the converse of all those angles, we have three more theorems. If two intersecting lines form a linear pair, so the two angles, let's call them 1 and 2, are a linear pair because they make a straight line. If they form a linear pair of congruent angles, so the two angles are congruent, then the lines are perpendicular. Think about why that is. If the two angles form a linear pair, then by the linear pair theorem, they're supplementary. So they add to 180. If they add to 180 and they're congruent, then each of them has to be 90. What does it mean to be perpendicular? Lines are perpendicular if and only if they meet at a right angle. Notice the if and only if. That is a biconditional. It's a definition. So if two lines intersect and form a linear pair of congruent angles, then the lines are perpendicular. Note the conclusion. With this, you're concluding the lines are perpendicular. The perpendicular transversal theorem. So some of these theorems get names, others don't. In a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. We'll look at this angle 1 and 2. If the lines are parallel, then we know that this angle is congruent to this angle, because if the lines are parallel, corresponding angles are congruent. And if one of them is a right angle, there it is, angle 1, then the other's got to be a right angle because they are congruent. Again, it is if in a plane a transversal is perpendicular to one of two parallel lines, it is also perpendicular to the other line. Again, note the conclusion. Then it is perpendicular to the other line. Last theorem, if two coplanar lines are perpendicular to the same line, then the two lines are parallel. This is the converse theorem you're using here, because if angle 1 and 2, if they're both perpendicular, the two lines are to the transversal, then those are congruent corresponding angles. And we know that if corresponding angles are congruent, then the lines are parallel. That's the converse theorem. But this, notice the hypothesis, if two coplanar lines are perpendicular to the same line, then, conclusion, the two lines are parallel. The rest of this video is just examples from the assignment. So if you're having questions, come back and watch the video, and hopefully that will fix any issues you might have. This is question 15. Given that angle 3 is congruent to angle 6, y is L parallel to M. You have to remember that if you're concluding that lines are parallel, that's the converse. So look at angle 3 and angle 6. Those are alternate interior angles. They're on alternate sides of the transversal, the line that crosses, and on the interior of the parallel lines. So this is the converse of the alternate interior angle theorem. Question 15. Given that angle 3 is congruent to angle 7, y is L parallel to M. The conclusion is that lines are parallel. That means you're using the converse. Look at angle 3 and angle 7. Those are corresponding angles. So this is the converse of the corresponding angle postulate. That's the only one that's a postulate. Remember, theorems are proved, postulates are assumed. And we try to assume the least amount of things we can. And it should be something that's supposed to be intuitively obvious. If you haven't noticed already, I did 2 question 15s. That's because these are all just different versions of the same question. So we may get repeats here. It's random. Given that angle 4 and angle 6 are supplementary, y is L parallel to M. The conclusion is that lines are parallel. That means you're going to be using the converse. Look at angle 4 and angle 6. These aren't congruent. They're supplementary. They add to 180. These are same side interior angles. So this is the converse of the same side interior angle theorem. Another question 16. Given that angle 1 is congruent to angle 8. Those are alternate exterior angles. So the conclusion is the lines are parallel. That means you're going to be using the converse. So this is the converse of the alternate exterior angle theorem. So on these, there's 2 answers. There's 2 questions. Which lines are parallel, and name the postulate or theorem that supports your answer. 12 is congruent to 6. So ignore the line in the middle. And we're just looking at line L and line N. Well, 12 and 6 are alternate exterior, with this line being the transversal. So this is the lines that are parallel are L. It's parallel to M. And the postulate or theorem that supports my answer is the converse of the alternate exterior angle theorem. Question 22. Given that angle 10 is congruent to angle 8, which lines are parallel? So we're ignoring line L, and we're looking at line M and N. Well, 10 and 8 are corresponding angles. So we know that M is parallel to N, and that is because those are corresponding angles. Since we're concluding the lines are parallel, the postulate or theorem that supports my answer is the converse of the corresponding angle postulate. Only the corresponding is postulate in both the original theorem and the converse theorem. Question 23. Given that angle 2 is congruent to angle 8, define those, angle 2 and angle 8. So we're ignoring this line right here in the middle. 2 and 8 are alternate interior angles. They're between the parallel lines. And there's my transversal. I know that L would be parallel to N. And that is because those are alternate interior angles. So it's the converse, because I'm including lines are parallel, of the alternate interior angle theorem. Question 26, angle 8 and angle 12. Angle 8 and angle 12. Those are corresponding angles also. So the lines that are parallel are L and M. L is parallel to M. And this is the converse of the corresponding angle postulate. This question is one students always have trouble with. But this is the idea that the shortest distance to a line is along a perpendicular. The line we're talking about, I'll put some points, is line AB. And I know that this point, let's call it C, the shortest distance to line AB is along a perpendicular. In other words, this distance has got to be the shortest distance. So any other distance to the line has got to be greater. And the other distance we're talking about is CB. I know that the shortest distance is along a perpendicular, so that means that negative 6x plus 6 has got to be less than 3x plus 10. Because this distance is along a perpendicular, it's got to be the least, the shortest distance. If we solve this, how about we add 6x to both sides? I get 6 is less than 9x plus 10. And now I'll take a 10 off each side. And I get 9x is greater than negative 4. And I'll divide both sides by 9. Remember that if we divide by a negative, we have to flip the sign. We're not doing that, so it's just x. And I'm reading it from the variable. The open side is towards the x. X is greater than negative 4/9. Now, if I turn that around, I'll keep the open side towards the x, is the way I like to write it. X is greater than negative 4/9. These two are the same. That would be the preferred way to write it. One more example, just like the last one. The shortest distance from a point to a line, again, the line I'm talking about is line AB, is along a perpendicular. So I know that the shortest distance is right here. That means that negative 8x minus 8 has got to be less, because it's the shortest, than negative 3x minus 2. I'll add x to both sides. Negative 8 is less than 5x minus 2. I'll add 2 to both sides. Negative 6 is less than 5x. And divide by 5. X is greater than, I'm reading it from the variable, the open side is towards the x, negative 6/5. I'm going to put the x on the left side, keep the open side towards the x. X is greater than negative 6/5. These two are the same. This is the way I would prefer it written. The next few questions are different versions of the same question, but dealing with the perpendicular theorems. Given the diagram that L is perpendicular to N, and M is perpendicular to N, so I've got right angles, L and N are perpendicular, M and N are perpendicular. Complete the statement. If two planar lines are perpendicular to the same line, that means they're parallel. Then they are parallel. Symbol for parallel is the two straight lines. And the diagram, what can you conclude? Well, that would be that L is parallel to M. Given in the diagram that L is parallel to M, so that one and that one are parallel, and L is perpendicular to N, so I've got a right angle right there. Complete the statement. If a transversal is perpendicular to one of two parallel lines, It's perpendicular to the other line too. Symbol for perpendicular and upside down T. What can you conclude? Well, that would be that N is perpendicular to M. Given the diagram and that angle 1 is congruent to angle 2, complete the statement. So I've got two angles that make a linear pair. Together they make a straight line, and they're congruent. If two lines form a linear pair of congruent angles, then the lines are perpendicular. Remember the reason: if they make a linear pair, then together they make 180 degrees, and if they're congruent, each of them's got to be 90. What can you conclude? That N is perpendicular to L. For the last few questions, you're just given the diagram. And what you need to realize is that all you know is that this angle is a right angle and that this angle is a right angle. There's nothing else you know. So what can you conclude is the question. Using the diagram, can you prove the statement that angle 11, that one, is congruent to angle 10? Well, they look congruent, but remember, can you prove it? Just because they look it doesn't mean you can prove it. So the answer is no, you can't prove it. You don't know they're perpendicular or anything there, even though they look it. You don't know the lines are parallel. Well, actually, M and N you do, because you have two lines perpendicular to the same line. That's one of the theorems. But over here, where you are, you don't know anything about 11 and 10. That line could be at an angle. It might be perspective. So for what reason? They're not congruent. You have to fill out both answers. So the angles are not congruent. Using the diagram, can I prove that angle 8 is congruent to angle 5? And the answer is yes, because those are vertical angles. That's the vertical angle theorem. That's your reason. Using the diagram, can I conclude that N is parallel to M? And the answer is yes, I can conclude that, because two lines perpendicular to the same line are parallel.